Okay, so if we look at fiber coating, it's the same basic dynamics, but the geometries are different. And the geometry is different actually in an important way. So since sufficiently important ways to change things, okay? So if we look at the curvature here, if we want to compute the divergence of the normal, so the local curvature, if the fiber is very small, then this curvature can be quite high. So we can define. So if we just look at it, the static case. So this is, the radius is B of the fiber. This is R1, and this is R2. Then our normal stretch. So in calculating the shape of the interface, so we know we've come to see that the shape is set basically by a balance between curvature pressures and hydrostatic pressure in a meniscus, right? But what happens in this geometry where we have a very thin fiber? So then we try balancing the two. Okay, so that's our normal balance, right? Inside the meniscus. So in the static meniscus, but if this thing, if the fiber is very thin, if R1 is very small, then this thing can get large. So in particular, if it's much less than the capillary length, then 1 over R1 looks like 1 over B. And, and this cannot be balanced by gravity. Okay? But happily, it can be balanced by this. Okay? Okay, so there is always a shape which has zero mean curvature, and that's a catenoid, right? So this has to take, if you have a very thin fiber, then this radius of curvature is so high that the only way it can be balanced is if this assumes the shape of a catenoid. Okay? So this is what a soap film, if you had a soap film, if you prescribe the tangential boundary conditions there and flat at infinity, that's what you get, right? So that's the surface which minimizes the surface energy. So basically, because this curvature pressure is so high, gravity can't save you. The only thing that can is curvature in the opposite direction. Okay? And so what this means is that the static meniscus on a fiber is not nearly as tall as the capillary length. So it's basically a small localized feature in which the interface takes the shape of a catenoid. So it's basically a surface with zero mean curvature. Okay, so if we have perfectly wet encase, so if the fluid comes in tangent to the film, so okay, and you have to have some cutoff. So in the far field, gravity will cut off this form to 1 2 LC over B. So this is in Degen's book. This is a text which I mentioned at the beginning of the class. Okay, so the thing to note here. So gravity only comes into play in causing this catenoid to extending to infinity. So you basically calculate H naught by cutting it off at the capillary length. And this H naught, so this is basically the vertical extent of the meniscus, is just on the order of B, right? So it's so it's basically capillary length, this logarithm of any, so maybe say this is 10 or 100, it's still going to be a very small number. So basically you get something on the order of B, right? So the vertical extent is comparable, in fact, to this. So it's really a localized feature. It's really like this, right? So it scales, so the meniscus on a fiber scales with the fiber thickness rather than the capillary length, right? Because the curvature can't be balanced by gravity, it can only be balanced by the other curvature. So the lateral extent okay, and there are actually some important applications of this. If you look at how they make the tips on atomic force microscopes. You know, atomic force microscopes are, you can get incredibly accurate measurements of forces, and they have this incredibly thin tip. And these are actually etched. So you start off with a glass fiber. so cylindrical glass fiber, and you submerge it in a fluid. And then as this thing gets eroded by the etching process, the meniscus retreats. And so you get at the end etching is chemical erosion. So basically this is an etching bath. So it's acid. So you're basically submerging a glass fiber in acid, and as it erodes, the meniscus retreats. Again, because of this dynamics, it doesn't stay at the capillary length as it would if it was a two-dimensional meniscus. So by virtue of the fact that it's a three-dimensional meniscus, the thing is going to retreat. Right? And it comes down, and so you basically etch to a point, and then you have this very sharp, something which is sharp down to. Yeah. So you'll etch. So it's basically what chemical erosion. So when you. Yeah. So etch. So. I'm sure Professor Nashman has used the line, "Would you like to see my etchings?" a few times, but it refers to you basically you take a piece of wood and you etch, so you can etch away the graphic, and then etch away a pattern, and then you roll ink on it, and then you print it, right? So yeah. Okay. Yeah, so these are actually you get incredibly accurate measurements of forces because these things are check. They're the most accurate microscopes. So and it's because these things are so small. They basically I need to check it out online, but I can't remember. I haven't run into them in a while, but I'll get back to you. Okay, so, but in any case, so the meniscus retreats. Okay, so in any case, in this new geometry where we have a cylinder instead of a plate, there's no longer a capillary suction, right? Because this has a zero mean curvature now, so the pressure in there is the same as the pressure there. Right? So again, optical fibers. So the entrainment is no longer resisted by capillary suction because the pressure in the meniscus is just the same. It's just atmospheric. it's pressure P naught there and there. Okay, and we know, but we know the pressure, so we know the pressure here. But there's still going to be a pressure difference, right? Because now we have a low pressure, a high pressure here. So this is going to be P naught plus sigma over approximately B. So because of the finite film thickness, there's relatively high pressure here. So there is a pressure difference between here and here, and it's that pressure which resists the emplacement. So pressure within the film. All right, so this is because of this curvature. It's augmented relative to atmospheric. Okay, so we can do the scaling now. So let's call this E. Okay, so this is viscosity. Okay, and so as previously, we can do a match of the static and dynamic meniscus. So once again, you find that this static and dynamic meniscus has a length scale, which is the geometric mean of the two lengths in the problem, but the two lengths in the problem are now this thickness and the film thickness. Okay? So we can substitute into our force balance. Atomic force microscope. I'm trying to think what. I think I've actually used one for something, but they're very sensitive. Like they can get. I think they can even measure, forces resulting from Brownian motion. But yeah, I think you're using it as a lever arm, right? The tip. So it's basically you're looking at the flexure of the tip. I need to think a little more. Okay, so sub and you get E, so thickness of the layer is on the order of the thickness times the capillary number to 2/3. Okay, so that basically gives you the thickness you expect for a fluid, for a fiber being pulled out of a fluid when the capillary number is sufficiently low. If you increase the pulling speed, so if we increase the capillary number, so the way this experiment usually looks is like this. You basically have a bath, and you have a fiber going in around some spindle, so it's being pulled at high speed. And in the viscous limit, basically what happens is you simply entrain fluid as you move through the fluid. Okay? So it's not determined by the local dynamics. There it's determined, you basically entrain fluid as you go through and you get this big, thick layer coming out. So the viscous boundary layer. So if you do a sort of so that's like a Blasius type boundary layer. You pull a plate and you the boundary layer gets thicker and thicker as it goes through. I think we've seen that scaling before. But in any case, you get the experiments look as follows. We plot E versus capillary number. Oh, sorry, E versus speed. So it goes like, scales as V u to the minus 1/2 in the high speed region. So here E looks like this guy, and here you have E increasing as u to the 2/3, and you have this turnaround around Reynolds number 1. So this is high Reynolds number, and this is low Reynolds number. Okay, so they're variant in terms of geometry, you can imagine. So there are other important processes that involve pushing air through confined geometries. So in particular in the oil industry, so how do they get oil out? They get oil out by pumping pressurized water in. So then you have the local geometry is oil stuck on the walls of a solid, and you're pushing water through. And so how much oil is left? I mean, this is, if you can decrease that by 5%, by 1%, you're going to make yourself a lot of money. So Okay, so this is the kind of geometry. So now imagine this is now a bubble. It can also be water going into oil, but we have some interface, surface tension sigma, and we're pumping this through at a speed u. So this is, imagine it's a cylinder with radius r. We have some ambient pressure P naught. And so the question is, how thick is H going to be as a function of the pushing speed? So this is, imagine this is vapor, imagine this is liquid. You can also imagine that it's, again, oil, water. So example, bubble, pipette. So that's a, and if you've ever set foot in a lab, you've seen that. But also pumping oil out of porous rock. So locally, you're going to have this situation whenever. So in some confined geometry with water. And typically, so as you do this with water and oil, basically the oil coats the side and you lose, basically 40% of the oil stays behind. Right, so it is interesting. How can you, what's that? Exactly, yeah. You want to make it as small as possible because this is basically lost in the process, right? So if by adding surfactants, you can somehow change these things, it makes a massive difference, right? And I think they do use surfactants, actually. What would surfactants do here? Would it make it better or worse?
I think they put like, I don't know, what...
So that means you're creating... So is that, actually, that would that... hold on. We have the opposite geometry from before, right? So we're creating surface here. It means you're going to have decrease the surfactant concentration here, which means it can be higher surface tension. So you can get an additional stress in this direction.
And maybe you could drive through viscous stress from the side, right?
Interesting question. Good one for a problem set. But sorry, Andre?
No, what? I'm not even bad at chemistry, so what do polymers usually do?
So polymers make the fluid themselves elastic. So there's a resistance to stretching. Imagine you put a bunch of, inside a normal fluid, you put a bunch of springs, right? So again, there's a resistance to stretching motions.
Yeah, this is the question you could ask me with Dan, my colleague Dan Martin.
Uh-huh.
I've heard him speaking sometimes of pumping water with mixtures, polymers, whatever, to get more oil out.
No, exactly. That would also, because the surfactants, I'm just talking about surfactants because that's the subject of the course. That's basically giving it a surface elasticity, right? But if you have polymers, then you basically have a bulk elasticity. And I think both of them will certainly change the...
Okay, so the polymer will give a bulk elasticity.
Exactly. So both of them will have some effect. I don't know whether it's good or bad, but I'm not in the oil industry. But I'm sure people in the oil industry know, right? And then there's the question of if you put some junk in, does it get into the oil, and then do you have to filter it afterwards, and are you actually gaining anything?
Yeah, can you do it easily, right?
Yeah. So okay, so let's try and get an estimate for how thick this layer is.
So John, this scenario, does it qualify as a Healy shock kind of problem or not? I'm also not an expert.
Yeah. So in 2D, if you have Healy-Shaw, you have a thin layer. Yeah. So,
Here's the two, right?
yeah. So you can do Healy-Shaw. oftentimes they'll have an interface. So you're just basically then pushing an interface. So there you have a plate, and you basically push an interface, but there you basically have something like that. So there's a contact line. Okay?
Okay.
Right? But you can do either.
And probably here you're going to have instabilities of a sort of fingery too, maybe, right?
Yeah, that's right. No, that's right. So I'm imagining here a cylindrical geometry, just for the sake of simplicity. So we have this R is the radius of our tube. So, and we're imagining if the thickness is much less than R, we can calculate the pressure gradient in the meniscus. Okay, so where L is the lateral extent, so sigma over R is basically the curvature pressure, and L is that's not that L, that's this L. It's the extent of the dynamic meniscus. So again, this dynamic meniscus is what you get from matching the static onto the thin film. So the geometry, so as on the fiber we can match pressures. So the guy who solved this problem actually is a guy, Bretherton, who is at Cambridge, and he, of course, got interested in these problems, and he's worked for a long time consulted a long time for Schlumberger, I believe. It's oil exploration. So basically H is much less than R, so we can just call that sigma over R. We can cancel these, and you get that the dynamic meniscus has a characteristic scale HR. So again, geometric mean of the two lengths in the problem, R and H. Okay, so the force balance so the viscous stresses are balanced by this gradient in curvature pressure so it gives us that H goes as R capillary to the 2/3. So again, the same scaling as on the fiber. So this is Bretherton. So again, C equals mu U over sigma, and this is the same scaling as on a fiber. Okay, and so the last, if you have, what happens if the thickness is not much less than R? So if you have thick films, Taylor looked at this problem. Okay, so if we have a situation like this, where the two are comparable, okay, and it turns out that the film thickness saturates, so this is as a function of capillary number. So it goes faster and faster, and the thickest will never go beyond 3.35. And the small capillary number theory gives you this asymptote. Okay, I definitely don't have time to do moving contact lines today, so let's call it quits for the week. Any questions? Problem set?
These kind of geometry only holds for vertical pipes, right?
What's that?
These only holds for vertical pipes, right?
Vertical doesn't come into it. Gravity isn't anywhere here, right?
The thing is that you have oil and you are putting them hot water, right?
Yeah.
So if there were standing like this, water would go always to the top.
Well, you're on a sort of scale, as we always are in this course, where gravity is not important, right? So you're basically looking at, this is flow in small inclusions, so millimetric. So if you have porous rock, for example, or sand, right, then you're basically looking at the flow through the interstices.
In that case, for example, thick films.
So again, if it's large enough for gravity to be important, yeah, you're going to get in trouble. But you can go to a larger scale just by density matching between the fluids. But true, yeah. I mean, there will be situations. You're basically implicitly assuming gravity is not important here. Yeah. So you can either do that by density matching or staying on a small scale. Question on problem set?
On the problem set, is the third problem. Is the problem that you have to consider red fluid and I don't know if you
Right.
have to consider.
Oh yeah. Okay. Yeah, I'll just draw a sketch. Yeah, I couldn't get my sketches onto my problem set, so that's probably unclear. But basically, what I wanted you to do is the equivalent problem of the soap film bursting, right? So in class we did the soap film bursting, right? And you got the Kulik speed.
No, my question was that
Okay.
you have to consider that the thread is short enough so you don't have to so you don't have the problem of Rayleigh instability.
Yeah, right. So, but that's the question, right? So in this, so if we start off with a cylinder of fluid, so this is again, right, this is a cylinder. So if we start off like this, we know it's going to retract like this at a certain speed. So I want you to calculate that speed, and then if you have the initial length of the fiber of the filament, you can predict how long it's going to take to collapse, and then you can compare that to the Rayleigh plateau time, because you know if we're starting with a cylinder, it wants to go unstable to Rayleigh plateau, right? So the question is, which is going to win? And so you expect. So the question is, when are you going to get just one drop, right? Or when are you going to get a whole bunch of drops?
And you can assume that when the water is scattering just at the ends of the steadily
So the problem is when the speed is going to win, it's going to be faster than the time that it takes to hold that Rayleigh stability to break.
Yeah, that's right. Right. Okay, so you want to compare the two time scales. So yeah, when does a fiber retract into a single drop, and when does it break up to many? Okay, very good. Have a good weekend. We've got